Hi, my name is Pablo Galindo.
And my name is Łukasz.
And this is the Core.py podcast, a new podcast where we discuss internals of CPython and other adventures in making a new version of your favorite programming language. Last time we discussed the original parser that Python used to convert your source code text into an ambiguous representation that can then be compiled into executable form. But that's history. Today we will be talking about the current parser, which is much cooler and enables powerful features like pattern matching and context-specific syntax error messages, which are very cool.
Right. So let's begin straight with some definitions.
We lost all the audience now. It's like mathematicians.
Right, yes, exactly. Like the biggest drop-off after 1 minute. Well, like the old parser was, so-called LL1, and this new one is called PEG. P-E-G.
Don't look it in Google.
So obviously...
It's not good.
The first thing that people will want to know is what is PEG? Like, what does that stand for? Well, so it stands for Parsing Expression Grammar.
Wow.
And, unlike the Dragon books of old and so on, like this is actually relatively new.
It's not on the Dragon book, not even in the new colors.
No, because this is from the 21st century. So this is new computing science.
Modern technology.
Yes, like 2004 is the year of Zen of Python. It's the year of Python 2.3. So, it's relatively new, right? So Python is older than this technology, right? Like that was written up in a paper by Brian Ford from MIT. And it kind of is a response to the Dragon book and the standards that we all used before. So it essentially says that, okay, you have context-free grammars and you have regular expressions. You can use them to parse things, and that's great, but those have limitations. So now, with PEG, with parsing expression grammars, we want to overcome those limitations. So, for example, thanks to prioritized choice, there is never ambiguity in the grammar. And context-free grammars had to be written in some specific way to avoid two rules to be kind of equivalent and making it impossible for the parser to decide which way to go. So here in PEG, you have prioritized choice, so that's not an issue anymore. The grammar selects the first match. So essentially the ordering matters, but that it makes it deterministic. It's not a die roll.
Yeah, it's kind of a trick, right? Like if you spend like years trying to find how to remove ambiguity, you can say, well, I will choose the first option and then the second option, and the one that works first then is the one that I will take. That is a way to remove ambiguity for sure.
Sure, like we're going to talk about this, but informally, tools were already doing this in the past. So only now the difference is that somebody actually looked at this with a rigorous mind and wrote a paper saying this actually makes sense. This will end up with a grammar that is consistent, cohesive, and you can express a lot with that.
Right.
The important thing is that this simplifies syntax definitions that you have. So you don't have to separate lexical and hierarchical components. It's just, easier to express what you want with the language that you're describing. And most importantly, you can write a linear parser for any PEG. Well, in theory, right? Scientists suspect that not all context-free languages can be recognized by PEG, but so far this hasn't been proven. This is a so-called conjecture.
Right.
So currently we don't know, but looks like it's good enough for Python at least.
Yeah, the world of parsers is quite in a difficult place to prove anything. Do you know that actually proving that two parsers parse the same language is the halting problem? Like it cannot be decided.
Wow.
It's not that it's very difficult, it's that it's impossible to know.
So you replaced the old parser in Python 3.9 with a new one. So now we didn't really know if we were parsing the same language.
No.
Actually, we did, right? Because the new one had a Easter egg, so it was already parsing something else that the old one couldn't.
We don't talk about that. It's secret. It's secret.
So we already knew that they're not equivalent. This is one way to solve this issue. It's like, is this unresolved? Do we not know? You have to break it on purpose. So now the answer is known.
Well, technically, the way we solve this problem obviously is throwing all possible programs and checking that the output is the same. But as you can imagine, maybe there is some mysterious program that is parsing differently. And actually that happened. I can give you an example at the end of the episode, so everyone needs to stick around. Oh no, tricks.
Okay. But before you get to those examples, like we're talking about parsing expression grammars.
Yes.
And you might want to explain to us what a single parsing expression is. Since I was going like from this bird's eye view saying, yeah, they're pretty cool, like, but what is a parsing expression?
Right. So a parsing expression is basically a pattern, and then you express this pattern in different ways. PEG normally has some mechanisms that are very similar to how we expressed it before, but you express this pattern in some way. You can think about regular expressions, for instance. And the idea here is that that pattern basically will match a given string. The string here is your program, or like a construct that you're passing, like a for loop or something like that. And either it parses it, so it matches or not. And if it does, it consumes the string. It means that it kind of like advances the parser to something else, right? So you have a for loop and it matches your parsing expression, then it will advance and it will say, okay, what is after the for loop? If it consumes or not may depend on what follows. So you can have like look aheads and whatnot, but we will talk about that later. But basically, it's just a pattern, and people call these normally rules instead of like parsing expressions because it's kind of like shorter. So when we say rules, are basically these patterns.
Yeah.
And then there is like the grammar, or what is technically called the parsing expression grammar. PEG. And here is just a collection of these rules that can reference, and they will, if they are forming anything that is not stupid, they will reference each other. And here the key is that they form like a graph. It's not like it's not a tree. And this is because rules can refer to each other, and then they can refer back. For instance, even they can refer to themselves.
Yeah.
So it's not like, as we said in the previous episode, it's not like Russian dolls one inside the other until there is like the smaller rule. These can refer one to the other, and then you can have either a rule can point to either another rule or what we call terminals, which are just simple words like for, def, if. Things like that, right? So the collection of
the things that are provided by the tokenizer.
Indeed. One interesting thing to say here is that, it's a bit theoretical. It's not that you can do anything with this information, but to get like a sense of the difference as well, because there is a technical difference than, PEG has the OR operator that is order and whatnot. But the key here is that one of the big problems with parsing expression grammars, and the reason a lot of people fear context-free grammars, is because context-free grammars are made in a way that will make easy to generate valid programs. So if you have a language that is expressing a context-free grammar, for instance, if like extended Bacchus null form or things like that, it's very easy to generate valid programs randomly. So you start in a rule and then there is an OR, so you randomly select one of the two and things like that. But generate a parser that parsers correct programs is kind of like going backwards. So that's why making parsers traditionally has been difficult, and then there's all these rules and all these things. But PEG is kind of like the other way around. Like PEG is like what the grammar describes is literally how to generate the parser. Mm-hmm. So generating the parser for the PEG grammar is straightforward. Generating random programs from the PEG grammar now is a bit harder. So it literally goes like the other way. So that's why making parsers with PEG is much easier.
I guess that's like a good compromise to have, though, because the thing that we actually want the parser to do is not to generate random programs, but to parse.
Right.
And historically, when we had LL1, it wasn't even really LL1 anymore. So when you are saying that, having this LL1 grammar allowed us to generate valid programs like, no.
No, it's false.
The grammar that we had in Python was a lie, right? There were a bunch of things that if you only relied on the grammar file, you would still generate invalid programs. Like the simplest example of this, if you had an assignment, the left and right portions of the assignment were using the same rule, and the rule was allowing you for way more things that are actually correct on the left side on the assignment in Python. Only the compiler later would find out if what you are trying to do on the left side of an assignment is a function call or something other that could be on the right side, but you found it on the left side, and only then the compiler would reject something as a syntax error. So relying purely on the grammar file, that would still...
Wait, Łukasz, are you telling everyone that the grammar file all this year have been a lie?
Worse yet, yes. Like when we introduced async in 08, the grammar was not even the full parser that we had. That parts of the parser will, in fact, put in the tokenizer. The tokenizer had to understand whether it is inside a function, which traditionally is insane. Like tokenizer is just supposed to tell you like, is what we are now being given is inside a string or not, or is it a keyword, like a strong keyword or not, or is it just some name, or is it some comma or dot or colon or whatever
number.
Yeah, but in this particular case it had to understand whether async as a string is on any given name, some random name, or is it our async keyword? And it did that actually looking at the context of execution. And the parameter for this in the tokenizer in C was literally called async hacks. So this is why the core developers wanted so badly to remove the soft keyword, even though in Python 3.7 that made adoption of the new version somewhat tricky to end users. I myself remember it was painful, like at Instagram, where a bunch of variables were named async, they were Boolean, or there were modules that were called async.py, and suddenly you had to actually do all this movement to get rid of this. But we didn't want this to be part of CPython because that kept part of the parser inside the tokenizer, which is an insane thing to do. It's super non-kosher. It's not what the Dragon book would ever tell you to do.
Well, it's even worse as well, because we were checking the code before, and it's starting the conditional async hacks block. Is the difference between the current location and the start of the token 5 characters, and is the first one an A, like from async, and then is the next token def?
Yes.
So let's say that this is async, and now that I'm thinking about this is now incomplete, because you should check also for like width, right? Because now you have async width and async for and async this other thing. So now it sucks, because you will need to check all these different constructs, and I don't think this hack will cut it in modern times. But hey, it made some good runs in 3.6, or it was 3.6, right?
Yes, that was 3.5 and 3.6 that had this. So 2 versions of Python, and then it was deprecated as soon as it was released, so we could remove it in 3.7.
Wow. That is the testament of open source, because if you do this at a company, you will be fired immediately. I've been working 3 months to insta-deprecate my feature, and it's called async hacks. How this will pass your code review? Vote on your phones.
Yeah, corporations have different rules than open source. Right, but that was LL1, and we already, I think, established it wasn't delivering on what we needed, even though, as you said before, LL1 was sort of primitive in certain ways, but Guido chose the grammar of Python in other wise ways, such that the limitations of LL1 weren't so apparent. Even though he did that carefully, this was not enough. So he had to switch. You remember that, how it came about?
Yes, actually, there is many threads. It's a beautiful story, because there is many threads that join in a single point and materialize in the peg parser. So I remember in the first core developer sprint that was in Seattle in the Microsoft offices, we were even there. I think it was 2017 or something like that. Yeah, and even then we were talking there about the possibility of having match. Because Rust is doing match, and the cool kids are doing this, and it will be awesome. And I remember, talking with you and Yuri about we should have match. But then the question appeared, Łukasz, what was the main problem of match?
Well, soft keywords, right?
Soft keywords, exactly. And we couldn't do it because everybody is naming their fucking regular expression match, right? Match equal re compile, whatever. So we couldn't name it match because it will break everyone. And we were even joking. I don't know if you remember, but I think it was Yuri or you who proposed that maybe we should use the facepalm emoji as the keyword, and then we will have the facepalm operator.
Yeah, because there is a pep that is this joking pep. But now we have Unicode identifiers, so we can express frozen sets as the snowman emoji.
Right, future. So that was one thing, and Guido was very interested in was toying with the idea of having this match thing, and he started to think about that, and he obviously knew that this was a limitation. Also, the story that we discussed the other day regarding the old parser, when Łukasz seduced me with his corporate powers to, break black in the future, that backfired a bit. But I think you also were talking with Guido about this, right? Like, so you tried several core developers to try to change it.
Yeah, and like funnily enough, we've been doing the LL1 hacks so long that everybody was sort of sure that something will work, that there was going to be some way that we can hack it enough so that it actually works in practice, And as you said in our last episode, it almost worked. Like there was just this one pesky case that was just, impossible to jump through with yield.
Yeah, I remember that I actually, we had that issue and we went back and forward and I finished the issue just proving that it was impossible. So we closed it just to revive it later.
Yeah.
But I think we just started to play with new parsers after that PyCon in which you talked to him. And he, someone suggested to him peg parsers while he was like researching different things, and he built like a very simple calculator because that's the first thing you do when you try a new parser, just to see how the calculator feels. And it's an interesting exercise. It's just because the calculator you can write it in different ways, and some of them are quite challenging for parsers. So you can have with a very simple language, the language of a calculator, you can have very complicated constructs and things like that. So you can have a very good feel over how difficult it is to construct a parser if you just write that language. And he really liked how it felt. Like he really liked how regular the parser was and how easy it was to debug. That was a very important thing. And he also felt that because Guido was a big fan of having the parser automatically generated from the grammar and have the grammar file as this is the grammar of Python. Is the legal text. So he was very confident that we could generate this automatically even in C. So at the same as we did with the old parser, just in a different way. So that's why he started to work on that, and because at the time I was just working also on parsers, I joined the effort as well as Lisandros Nicolau, and Emily also helped a bit here. And that's how we started to work. We did most of the work in the first core developer sprint at Bloomberg, I think, well, the first and only. And then after it took us a year from start to end to do everything, including the pep.
Okay, cool. So my initial question then was, when we discovered that LL1 was not sufficient, then why not use what the Dragon Book tells you and what everybody else tells you, which is to use LALR, so essentially what the default Lex and Yak tooling provides, and Bison right now and whatnot.
Those are ancient tools for a more civilized time.
Yeah, but it turned out that even in more civilized times, Guido's initial gut reaction when he started working on Python was that there is something wrong with Bison and Yak, and he just didn't like it from the get-go. There are those things about parsing in Bison and Yak, how you either shift or you reduce. And as we said, with context-free grammars, you can get to situations where two things are equally likely and you cannot decide which one you should go and choose. So those are called by Bison and Yak conflicts. And there's shift-reduce conflicts and there's reduce-reduce conflicts. And Guido didn't like the fact that you had to solve those by either wrapping rules in other rules, and now magically something that was a conflict is no longer a conflict. But even worse, Bison has literally directives, and we were already talking about this a little, where you can say that actually prefer whatever comes first in the file.
Right.
So the thing that is now formalized in Peg, you could already tell Bison's it's fine, just prefer the first thing that it comes. But the documentation of Bison tells you this is evil, you shouldn't depend on this. But then if you find any non-trivial grammar like in Bison, you will always find this exception somewhere where it essentially says that you should expect this. But better yet, there is this other way to silence the warnings about conflicts by just saying, if there's exactly n conflicts, then it's fine. So you specify the number and
Six
say
errors are not an error.
yes, exactly. So essentially, like Guido didn't like this. Like he felt like this is ugly and unwieldy, and it's hard to come up with, solutions for those conflicts, and that limits the expressibility of the language that you want to implement. But even the metagrammar, so the actual language that you are using to describe the grammar of your language, that was somewhat annoying in the Bison and Yak tooling. It didn't have some of those organizing like parentheses that allowed you to group things and say there's going to be more than one of those and so on and so on. So expressing those was annoying because you had to, again, make other rules just so that you could say there can be more than two of those and so on and so on. And that made the entire grammar file of a language much bigger than it needed to be, just because that metagrammar, so that language of what you used inside the grammar was the metagrammar, like the yeah, so that was not powerful enough.
Not powerful enough. I have a suspicion as well. This is not official. It's just like my guess. But like I think, and I don't know this by myself, because like as everybody knows, my background is physics, not computer science. But I'm told that Bison and Jack have traumatized entire generation of computer science students when they do compilers or formal languages or whatever the course is, because basically the course is implementing one of the stupid languages using these two tools. And I guess Guido is also included here. That's one of the reasons probably he doesn't like this, because those battle stories have to be like crazy. So yes,
that makes sense to me.
But like there is some cool things that these tools make stupidly difficult as well. There is ways around, and most of the big languages. By the way, like I think Ruby, for instance, used to be written in some LexJack, and I make a look at the file, and it's just a monstrosity. So like these files are like C files and like definition files from Jack that are like super big. We're talking about like thousands of lines, and like it's really, really difficult to read. I'm saying this when the Python grammar is also, I think, 1,000 lines or something.
Well, but now it is, but like to be clear, like a lot of it is comments that move explanations from the PEP inside the grammar file, so that you don't have to look at the PEP while reading. So
and we have all the error location, blah blah blah.
Yeah, so like that's somewhat of a different case, I think. Like the core grammar of just the language is way smaller. But like if you're honest, right? Like if you're honest, then you have to say when PEG was chosen, I was immediately also deemed like insufficient in how it is described in the paper that defines it, right? Like there had to be some innovations that Python did to make PEG work for what we needed. So like what were the innovations? What did you have to change?
Well, one of the things is that PEG is just very bad in performance-wise. In the paper, what it describes is basically an exponential parser. So parsing any string will take an exponentially big time given the length of the input. So like 1 takes logarithmically lower than like 10, right? So it's bad. So one of the things that we needed to do that, fortunately, because this was 2004, like there's a lot of research since then. And one of the things that people have done is like to ensure that, parsing can be done actually. So there is this techniques that we will talk in a second that basically tame a bit the complexity of running the parser from exponential to linear. So that was one thing that was easy because like mostly everyone does this thing called backward parsing that we will talk in a second. The other thing is not necessarily needed, but like this is something that, now that we're working in the parser, we really wanted, is to have something called left recursion. And left recursion is this idea that a rule can start with itself. For instance, the calculator, again, it's a language that you can write like left recursion.
Yeah.
And this is, for instance, also used to encode the order of operations in the grammar. So again, if the calculator, that multiplication takes more precedence than addition. So you have, 3 plus 2 times a. So the multiplication at the end is done first, and then you add the first number, right?
Of course.
So that can be encoded correctly if you write your grammar rules nicely. And one of the best ways to write them is to use left recursion. So for instance, if you just focus on the part when you're describing addition, just addition, you will say that, an expression is an expression plus a term when, expression is again an expression plus a term, an expression is again an expression plus a term, or a single term.
Yeah.
So basically what you're saying is that, addition can be something plus something, where the left part can be more complicated, or something simple. So term, if you can imagine in term like number. So you can say like, like addition can be, so expression can be expression plus number or number. So, a number it was like 3. So that will be just that. But it can also contain like another one. So you have plenty of, plus signs together. So 1 plus 2 plus 3 plus 4. You can call the rule again and again and again, and it will keep parsing from the left.
Oh.
And that can only be done if your language allows you to express this recursion nicely, because like most parsers will, parse infinitely, will not even attempt to parse any number, because they will say, oh, an expression is an expression plus something. Oh, what is an expression? Oh, and they will keep, going down the rule until they crash. So this is something that we really wanted to have. And PEG doesn't really allow this, because what PEG, basically, the way you will write PEG parsers is to have recursive parsers, and recursive parsers technically normally are not left recursive because of this, because they will keep asking like, what is an expression? What is an expression? So we needed to have some tricks. That fortunately, there was some research, although not super popular. So this is like on literally bleeding edge. So Guido came with like some like slightly different architecture for this. Apparently, we were told that as everybody does in academia, there was some person who already had some previous version. Ours is a bit different, we have to say, but the idea was already but the paper was very recent. It was like 2013 or 14,
wow,
or something like that.
Okay.
It was growing the seed, and that's the original version of this algorithm. But Guido came with this slightly different idea that was more tied to how we were constructing the parser, so that allowed us to both implement memoization and left recursion in the same go.
Right. So that's very cool. So now we actually do have the new parser. What are the less obvious things that this new parser allowed that we couldn't have before?
Well, one of the things, for instance, that we were a bit worried is that this memoization was making the parser eat more memory, but we were plenty surprised when actually it took a bit less memory. And one of the reasons, which is an advantage, because this also makes it much faster than the other one, is that this doesn't generate an intermediate tree. So the previous parser, as we discussed in the previous episode, before generating the abstract syntax tree, which is the kind of representation that the compiler needs, it generates this previous representation called the concrete syntax tree that will include things like commas and like, other things that are not really necessary. And then there is like this process that will take the concrete syntax tree and it will transform it into the AST. That process was written by hand. And what we say about code written by hand, especially in C99,
it's buggy.
not only buggy, it's now illegal. Illegal, yes. The U.S. government, the U.S. government saw us this beautiful document that says that now C and C++ are illegal. You cannot write C and C++ legally now. We are screwed. But then the U.S. government will be happy to know that well, yes, it's C, but it's automatically generated. So it's like machine written, not learning, but written. It's another verb. It has to work. So the advantage is that, because we generate less things, then it's faster, because doing less things is faster than doing more things.
Of course.
Wow. So that is very good. The other thing about having manually written code that transforms one tree into another tree, apart from, this could be an interview question, but it was not, it was CPython, is that it had a lot of little problems because, it's written by hand. And C code written by hand that transforms trees is very hard and it's impossible to have right. So one of the things that you needed to do when you were transforming the trees is to keep the location of the token. So, this token goes from this line to this offset to this line and this other offset. And that was done by hand. And, it was full of mistakes, but nobody cared because those locations were not used for anything. But then, we had this cool PEP that has this horrendous name that I will regret for until the end of time, which is PEP 657, include fine grain error location in tracebacks. And this is what allowed these nice, error location tracebacks that we have in 311, 312, and more. And this uses these locations. And because, the previous locations were done by hand, all of the locations were wrong. And we will have had like gazillion, bug reports of how like this is not useful because it's wrong. But because now this is all automatically generated. All the locations are magically correct because the machine doesn't make mistakes.
That's what the machines want you to think. Yeah, but what else?
Some other things is that, we can have this funky syntax like parenthesize context manager and break different formatters. That is kind of cool.
Yeah, very cool.
But the other thing, which is less known, is that let recursion, apart from, allowing you to write these rules a bit better, allows you to avoid another kind of hack that we have with LL1 grammars.
Yeah.
And the problem is that the LL1 grammar is also not possible to have left recursion. Oh no. So how we solve the problems? Well, there is like a bunch of techniques that you can do when you cannot have left recursion, because, if you can write calculators, then your parser is just a bit stupid. So for instance, for the calculator example, when you will write an expression is an expression parsed a term or a term. So instead of writing that, because that is left recursive, we will say that an expression is a term and optionally a sequence of 0 or more plus terms. So basically, you're saying the same thing. This rule basically parses 2 plus 3 plus 4 plus 7. So you're saying that it's either one or multiple ones, right? When you have like plus something at the end.
Right.
The problem is that the first one, this one that I'm mentioning right now, that has this 1 or 0, 0 or more repetitions of plus and term, generates a linear tree because it's, term, and then you add more stuff at the end. So that's not what you want.
The order of operations is not preserved.
Exactly. So you have like a big array when you have the tokens 1 plus 3 plus 4. But that is, you are not reflecting the order. The order is from the right? And then you have multiplications, you want that. So you want like a tree that is plus, and then it has two childs. One is 3, and the other is another plus. And then that has two childs. One is 4, and that's another 3. And that reflects the order. The compiler will receive this tree and it will immediately create bytecode without having to understand that multiplication takes precedence and blah 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 blah. So before the transformations from the CST to the AST needed to do this extra transformation to transform this linear array into the tree version. And now we generate the tree immediately. So that makes not only the code much easier, but it's also faster because you need to do less work.
Yeah, that's pretty cool. What is less cool though is that now with the parser, Python could now grow new features. And the original motivating example with the with statement having multiple elements that had organizing parentheses was one of those things that we've proved was impossible to be parsed with LL1. And then we added match statements with cases and this DSL that you have in a case. And that's, again, something that would be impossible with LL1. But guess what software was written using an LL1 parser?
No, it's impossible. Are you telling me that Black was using LL1 parser?
Oh, yes, it was. So now, because of my complaining, one of the things, obviously, that motivated the parser, maybe the smallest one, but one of those was my complaining. Black kind of shot itself in the face. Not even in the foot, no. It was essentially, haha, now you have to rewrite the tool. But wait, was it rewritten?
No.
No. But can it actually parse parentheses with statements?
It has async hacks, I'm told.
Oh, yes. And can it actually hack match statements too? Yes, it can. But if you look inside...
At what price, Łukasz? At what price?
Well, at the price of Batuhan Taskaya's sanity, because he was the person that implemented those hacks inside Black's parser. So if you squint enough, you're going to see the same tokenizer insanity that we had with Python 3.5 and 3.6 for async and await in CPython. Now, when you recognize that there is a match word in a source file with Black, you're going to have a modified grammar and a modified tokenizer that has a so-called token proxy, and that token proxy emits things until it finds, there's a match. So now it will stop emitting tokens, but it will see what happens next, and it will consume the incoming file. What happens next until it finds something that would be invalid
Jesus
in
Christ,
a match
man!
statement.
This sounds like a deal with the devil. Like this is you are just describing the computer science version of corruption. Like this is just it's really
Yeah, it's not something that we wanted ever to have, but it was sort of, either that or rewrite the tool from scratch, which would be way worse for the users, since there would be no way to write it in manner so compatible that people can just switch from that to the new version without any disturbance. Oh wait, isn't that what Charlie Marsh did? Nah, doesn't matter.
Nah, we don't talk about
At the time, we didn't know. Like, we weren't so confident that this is actually something that can be done. So the hack was used instead. And, it is actually interesting in more than just the tokenizer hack, since what Batuhan kind of understood and realized was that we are still using the AST of Python to check whether what you're producing before formatting and after formatting is valid. We still do this, right? So we can assume that there's going to be some part of Black's pipeline that will check whether your code is valid. So inside our match parser, we don't have to actually parse the language as described in the grammar of Python, because that DSL is more limited. It doesn't accept any expression inside the case. But we don't care, right? Because the AST will find later if somebody would actually use something that is not really a match statement. But in Black,
string coupling.
Yeah, in Black you can actually have like crazy things inside the case expressions, and it will be fine until you get to the AST, when actually Python will tell you this is invalid.
Man, I have so many things to say to this. I have so many. I knew the basics of this hack, but Batuhan. I remember I promoted Batuhan, so I admire his resilience to solve these problems, but I knew the whole story, and I have so many things to say now. We don't have time, but I want to say that now, normally you will say, Parser is so complicated that you need to split it. Now you have this nice, definition that is like, you have the tokenization, and the tokenization only does this thing, and then the parser only does this thing. But now the names don't mean anything to you, don't they? Like, it's just like a blob. It's like, I will parse for you. Like, it's like you will do this thing. And the other thing I have to say is that I have this beautiful discussion the other day, because when we adopted Black and my team in Bloomberg, everybody was scared of Łukasz Langa, the bringer of doom, and like, what if we format all these files and it changes the semantics of the code. So I implemented this GitHub bot that will parse the AST, and it will say the AST didn't change, so you don't need to review this code. You can just merge it, and it was beautiful. And then, that was done, and the GitHub bot was there still, but it was abandoned. And the other day we were just saying we should remove this bot, right? Like, it doesn't do anything. And I was like, well, it's kind of cool. You can still do it. And you pass a formatter that is not Black, like maybe, RAF or whatever, then you can check. But then I was told that apparently Black doesn't check anymore if the AST is preserved, right?
Oh, no, that's not true. So that was the only thing that actually made people adopt Black, and I actually wanted it for myself too, that we checked whether the AST is exactly the same before and after.
You still check it these days?
Life always interferes. Life is just pragmatic. And even the Zen of Python says things about pragmatism. And in our case, the pragmatism was very simple. Google-based code that used 2 space indents that was later reformatted with Black was reformatted nicely, except for one place. All the doc strings were now indented wrongly, because they were multi-line strings, and inside the string we don't touch anything, because that is part of the AST. We would actually find that the AST is different now. This is semantic difference. This is content. No, we're not touching this.
Right.
But we got hammered by requests of people like, hey, you need to fix this. Like, this is wrong because, I also don't want to nicely indent my doc strings. I want Black to just align them with my function signature. And there was so much prominent feedback about like, no, this needs to be part of the formatter, even though other formatters didn't go as far as to actually look inside doc strings and change them. But people are like, no, Black needs to do this. If it actually wants to like enforce everything, doc strings need to be re-indented too, not reflowed, right? We're not gonna put next extra new lines or remove new lines, like no, but just reflow them so that they align to the function below which they are.
Yes.
So we did that, but now there was this issue. Well, obviously this entire AST check will not work anymore. So there is one exception in the AST check that just is about doc strings. We will now like have the check, but the doc strings are going to be compared as if they were not reflowed, because we know that, okay, this is this one check.
But doesn't this force you to re-implement the whole AST check?
No, there's a visitor post creating the AST that just says like for doc strings, which by the way, like have specific place in the AST, so they're trivial to find, they're semantic.
Well, but this is a lot of words, Łukasz, but this means that my bot is broken. Because my bot will fail. It will check the AST before and after, and doesn't have this stupid exception.
Well, but that only happens like once, and then you can probably just ignore that failure for reflowing code that is coming from some pre-existing formatting.
The important thing is that I broke you, and then you took revenge. This is what happened.
I don't think that was revenge. But still, yes, rightfully, probably, there are people that say, yeah, this is no longer true, that Black is not changing anything because it's going to reflow my doc strings.
Well, I cannot wait until they learn that in 3.13 we automatically did doc strings. It's secret.
Okay.
It's not breaking anyone.
Don't tell anybody.
No. Python may or may not change the doc strings in 3.13.
All right, so but this is not black.py, right? In fact, there is no black.py anymore. For the longest time, I was like, this is fine as one file.
Oh, come on, you also destroy the file. No, this is depressing.
Let's split. So yes, that's depressing. Let's talk about the PEG parser again.
You're compromising core formatter, my ass. No, I compromise everything. Boo.
Okay, we have the PEG parser now. So the one that we had before was very easy to understand. The one that we have now is a little more tricky.
Let's speed run the actual part that people want. So that's let's surprise everyone by not doing what they want. So let's explain how PEG parsers work.
Yes.
Okay, so it's very simple. So you have rules, which are these like almost like regular expressions, like they actually feel like regular expressions. And then the idea is that in those rules you may have the OR operator, which is this pipe, this vertical bar, and that allows you to say, well, this rule can either be this or that. And the important thing now is that instead of using math and complicated algorithms to know which of the option is the correct one, you will try one, and then you will try the other, and the first one that works is the one that you get, and that is it. And the idea is that when you are generating a parser for the grammar, every of these rules is a function that you will write. And when that rule calls another rule or refers to another rule, that's a call that you make in the parser. And the call will basically say, yes, this rule matches. And in that case, it will return a null in the AST or whatever result you have. Like if you're doing a parser that just checks if it's valid or not, it will return true or false. But you can also return like the AST, and then you construct the AST as you go. So it will return something or it will return nothing. So in a normal parser, returning nothing is an error. It's like, meh, because the math will tell you if it works, and if it doesn't work, then nothing works. But here, because we say that you need to try one and then the other, returning nothing just means, well, this didn't work, maybe the next one will do.
Yeah, try the next one.
Exactly. And this is what we call, one of the consequences of these simple statements is that this now has infinite backtracking, because this try this. When you pile one rule after the other and, this is done recursively, now that allows you to have infinite backtracking. And that's the whole idea. And the whole idea is that you go, you say you have three possibilities, so then you have an if condition with three possibilities, and that's it. And then you try one and then the other, and it's an OR. So the first one that works is the first one that you get. Funny enough, if you are implementing this in Python, this construction, allows you to use the walrus operator, the forbidden one, in a very nice way, because you can have an if that will check the 3 options, and using the walrus allows you to get the first one that matches if you have ORs in the middle.
Wow.
Incredible. But this also allows to have a bunch of funky stuff that you couldn't have in the previous one that also feels like regular expressions, but not all regular expressions, only the cool ones. So you can have, for instance, look-aheads. So you can say, this rule will match, 4, and then something, only if that something starts with, the letter P of Pablo. Wow, how is that possible? Well, because you can literally parse that and then go back if it's not true. The previous parser couldn't do that, even if it sounds very simple, because it uses math on these algorithms, and that's boring.
Yeah, it had 1 token of look ahead.
Yes, but now we can have all the tokens, because you can have an entire rule in the look ahead. Wow, how is this possible? So you can literally write a stupid rule, and the stupid rule will check your thing, and if that rule is true, then it will work, and if not, you will go back and try something else. It's just fantastic. It's super easy to do. It only has the kind of problem that it makes the whole thing very slow. So that's kind of problematic. Exponential time, it may or may not be the worst complexity that you can face. It's kind of bad. Technically, it's not exponential, but it doesn't matter, because when people say exponential, they don't know what they are saying. There is potential and then there is exponential, 2 different things.
And impotential.
Yes. This actually grows like n to the power of n. So not e to the power of n. So it's actually faster. It doesn't matter. So, but this allow us to, what comes next. So do you know where we use this Łukasz?
The what? The look ahead?
The look ahead. One place when we use the look ahead in the grammar.
Well, for sure, you need to use this for the with statement that we were talking about.
Yes. Bingo. That it is, because we say, is this followed by a parenthesis or not? And then we can decide which one of the 2, which is funny. By the way, one funny thing that is just fresh news here. This is literally yesterday. We learned this the other day. Well, not yesterday, but last week. Apparently, we found the first difference between the old parser and the new parser.
Oh, really?
Wow, it was something that was not parsed the same. Wow, what it is, Łukasz?
I don't know. Tell me.
It is related to the context managers, and you will see immediately. So apparently, before, in the old parser, you couldn't have parenthesized context managers, but you can try. And something that you can try to do is to write with parentheses, open or something there, I don't care, comma, and close parentheses. And that is a very stupid thing to write, because that is a context manager with a tuple in the context manager. And that will never work, because tuples that have enter and exit, but it's technically, syntactically valid, but now it's a parenthesized context manager, a totally different beast.
So you will never get the tuple.
So now it's not a tuple anymore. Now it's a parenthesized list of context managers.
Okay.
Semantic difference. All was a lie. Well, if someone was trying to put tuples in context manager, now he's crying on a corner, but as that was invalid, we don't care. I actually checked my notes from the time, and we knew about this, and we didn't care. And now we learn again. But yes, one of the things that happened with this, try this, try that, and going recursive and infinite backtracking, is that infinite is a very big number, and it's kind of slow. So the way you yes, infinite is very big. Did you know that there is very different ways? There are different infinites. There are infinites that are bigger than others.
Oh yes.
Yeah, Alephs. They are called Alephs. So Aleph 1 is bigger than Aleph 0. Wow.
Yes.
Yes, incredible. This is Aleph Omega, which is even a different infinite. It's true. There is the ordinal infinite and the cardinal infinites. They are different. That doesn't matter. We will talk about it another day.
But what's this Aleph? Is this Hebrew?
It's a Hebrew letter. It's like N with a lot of it's in a cold day, because trembling, it's like trembling.
Yeah. Okay, so that's
it represents the number of natural numbers. Aleph 0. And then Aleph 1 is the number of real numbers.
Okay.
How many real numbers there are. Yeah. Both are infinite, but one is bigger. It doesn't matter. So yes. So how do we make this infinite not infinite? We use a cache, because that's what you do. It's not Redis. It's an actual. It's like a linked list, because we are writing C, and illegal languages use linked list.
Right.
So our cache is like a very fancy linked list with some tree shape. But it doesn't matter. We use this cache, and the cache basically will tell you if an entire parse that you tried before will work or not. Because as you can imagine, if you try again and again and again, and then you go back to the previous rule and then you try again and again and again the same thing, you don't want to parse the same thing twice.
Right.
You know it's going to fail. So we cache basically the results, and that tames the parser. You can prove it. Actually, it's a cool mathematical proof. You can tame this into average linear time, which is what you want. You want things to be linear with the number of tokens, which is kind of cool.
Very good.
And we also use this cache for the left recursiveness. It's a complicated algorithm that I'm not going to describe here. But caches, what are the problem with caches, Łukasz?
I don't think you mean cache invalidation. You probably mean memory consumption.
Yes, they like memory. No. They eat a lot of memory, and memory is bad. We didn't like memory. It doesn't matter really because like people don't care about memory. But you know, GPUs are eating like entire cakes of memory. But we kind of care. Like we like to do cool things. It turns out that even if most people that will tell you that you need to use this cache, by the way, this algorithm is called pack-rat parsing. That's the technique.
Yes.
We learn very quickly through reading sacred papers that you don't need to memorize everything. You only need to memorize what is called the chunky rules. And that is not a technical term, that's my term. And the chunky rules are rules that will eat a lot. So it's basically if you plot the graph of the rules, are rules that have a lot of arrows. So, you know, they eat the arrows, they are chunky.
Okay.
So we created a way to say, okay, this rule is memoized, this rule is not. So that is great because you have less caches and you still have linear time.
So you say at chunker.
Yes, at chunker. But it's called memo. But we still have a chunker.
It's boring, yes.
Chunker. But something can go wrong. It was a rule that should have been memoized and it was not. And that has a problem. For instance, if you write the sequence of 15 open curly braces and then a colon, which is invalid Python, as you may know, Python will nicely parse recursively the whole grammar 2 to the power of 15 times. That is kind of like not too bad. In modern processor, that is actually like fast. It takes like 15 seconds or something, like 2 3 seconds. Sorry, but it turns out that if instead of 15 open curly braces, you add like 30, it takes 1 hour, and probably if you add one more, it will take like 2 hours, and that goes because it's n to the power of n. And that was an actual bug. It was BPO 46707. You can go out there. It was reported by Anthony Shaw. I remember. I don't know what he was doing. He found this. But he reported it, and then we solved it by adding a memoization cache.
And did you tell him like it's not exponential actually?
No. He already knows that I'm annoying. I don't need to prove it.
Right. One thing that you mentioned about the grammar file is that we still have like one that is pretty big now, but you mentioned that some of the rules in there are not used every time, that they're very specific. So what I discovered is that yes, in fact, there are 2 passes of the parser, right? Like you have the one where we are parsing some valid Python program. So it's going to parse, it's nice. We know how to turn it into a tree. Now we can compile it. Now we can execute your code. It's fine. But if we fail for whatever reason, because that first pass of valid Python is not possible, then we turn on additional rules that allow us to do what you introduced to the language, right? Which is the nice syntax error messages that tell you exactly what you did wrong. Whereas LL1 used to be extremely confusing when you were forgetting a closing paren or forgetting a colon or whatever.
Right.
So now there are 2 passes, and the second one allows for nicer syntax error messages. So there are, in fact, macros like that are called literally raise syntax error known range, raise syntax error on a next token, raise syntax error, raise indentation error, and so on, that allow for those specific error message cases. So tell me, how do you come up with describing a grammar for mistakes that people make? So how do you go about adding a new thing there?
By suffering. That's the way you do it. It's actually a very hard problem. We actually try, by the way, trivia. We try to do this automatically, and then we quickly learn that it's very stupid. Because like, if you do things, like I had this idea of like saying, every time the parser will try to parse something and fails, you will remember that. And, the farthest failure point, you remember all the tokens that could have made the parser advance, and then you will tell the user, well, this is as far as I went, and if you will have given me any of these tokens, it will have been nice, that sounds like a great idea, right? But then the error message will be like, hey, a syntax error. Maybe you mean one of these 16 different possibilities. Like maybe it was 4 or maybe it was if. What about this colon? Like it was so stupid that when I tried this rule and then I just say, oh, it has this small problem that sometimes it just shows you all the possible tokens in the grammar. Like for instance, if you make a syntax error that is like a bunch of backlashes, that's bad. It will tell you, well, I expected everything, and it will just print everything, all the possible keywords and tokens and shit. But one of the tokens that was there was the Easter egg. Like the _peg _parser that used to be the Easter egg was a keyword. So it also said, maybe you mean _peg parser. And Guido was like, yes, let's do 2 things. Let's not do that, and let's also remove the Easter egg. Oh, yeah. So I destroyed my own Easter egg. But yes, that is bad. So it turns out that you need to like do a superset of the grammar that will try to detect what the user is writing wrong, which is surprisingly complicated because like you need to parse all the ways to write incorrect Python. So that is obviously impossible. So it's like a best effort kind of thing. So there is a lot of theory here that we don't have time to go into. Because like if you do this in YOLO mode, you will suffer. Like it's super hard. It's very easy to just destroy yourself because the rules will basically like annihilate each other and it will compete with each other to parse syntax errors. So you have syntax errors that have more precedence than others, and like it's exactly. If you do it badly, it's basically a whack-a-mole game. So there's like a lot of structure, and also by the way, there is like a bunch of like hacks there. Strategies. There's a lot of strategies there.
We no longer have hacks, right?
It's secret. I mean, it's documented there, so you read it. There is nice comments that will explain you the whole thing. But like, is this kind of thing that as a programmer, it will make this like feeling in your spine, like, ugh. So like, why? So for instance, you can name your rules whatever you want. You can say this rule is a for loop, and you write for _ loop, and that's it. That's the name of the rule. Well, it means nothing. It's just the way you will use to refer to the rule in another one. So you say expression is for loop, so you will use your name.
Right.
But Łukasz, this is secret. This is like the first time this is revealed to everyone. If you made a rule that ends in without invalid. Then the parser will magically know just by looking at the rule name that when it parses this rule, it will not try to parse invalid rules underneath.
Nice.
Wow. And this is how I allow like these conflicts to be resolved sometimes, because you don't want invalid rules to invoke other invalid rules sometimes. Other times you want to.
Yeah, or valid rules invoke the invalid ones, before you tried actually every option, right? Because then...
Yes, valid rules not invoking the invalid ones is done by these 2 passes. So the first time you pass, the invalid ones are never tried. None of them are never tried. Well, technically that makes, by the way, the second hack, because like if a rule is called invalid, then it will be identified as an invalid rule that will not be tried in the first pass. Right. Which is also made by name. So, once you do one convention, you can do the second convention. There is other conventions that are a bit nasty, but this is one. And this works quite nicely. It's just that, you need to be a bit careful when you do it. So it's not just super, super, super easy, but it's certainly much easier than doing it by hand. And it's certainly much easier or better than doing it automatically. Because automatic errors in your parser suck. If you have any parser whatsoever that will tell you, our super cool technology allows you to have these super nice error messages automatically, they suck. They are bad. Don't get fooled. It's just bad. They are like things like, oh, there is a colon missing here.
Okay, right. One thing that I'm wondering about is that the old grammar file used to describe the rules and how they related to other rules, and that was essentially it. That was essentially the content. The new grammar instead also has bits and pieces of C code. Some parts of the rules have assignments to variables, and some rules have declared return values. So what's up with that? What's all the C code doing in the grammar?
Well, those are the actions. They're called grammar actions. It's something that I think other parser generators have, so it's very popular. And the idea here is that when a rule succeeds, then you have to return something if the rule succeeds, or nothing if the rule fails. But the something can be anything you want. If you are building a parser that just checks if something is good or bad, then you return true or false. But you can now return an entire tree. And in particular, to construct that tree, you need to run some code. And the actions allow you to literally tell me what code do you want me to write when the rule succeeds. And because rules are calling other rules, that is a recursive process that makes the whole thing perfect to write something that creates a tree. because trees are created recursively, and the actions are basically a C code that is copy pasted in the generated code that will be run only if the rule succeeds, and that's the way we create the tree. So we have a bunch of functions in C that allow you to create this node or that node or the other node and this thing, and then when you write in the grammar, you tell me what node do you want me to create if the rule succeeds, and because the parser generator is going to generate C code, then you will just copy paste your C code, and that can be a function or something like that. You don't need to write obviously 5 lines of C code. It can be just one function call,
right?
And that allows you to write literally the final parser just by reading the grammar.
So in the rules, you can specify what return type given rule is going to have. So that function is going to return some C struct. So this is tied pretty closely to C, but in the pep it says that the thing about the pep parser is that we can generate both C and Python code from the grammar. So if you have bits of C in the grammar, like how can you emit Python code then?
Well, I mean, you cannot. That's the way, if you want to generate Python, you need another grammar that has Python in the rules. Funny enough, we have the same parser generator for both Python and C. It's just that the backend is different. So, you parse the thing, and then when you generate one of the others, you use 2 different backends. But the original grammar that describes what is possible to write, so how you write the grammar itself, what we called before the meta grammar, that is written in Python and is tokenized as Python code. And one of the one of the consequences is that if you go to the generated C code, all the words are space. So if you put like x dot y, it will be x space dot space y, because it's tokenized as Python code. And the only way to write that back as C code is doing space dot join.
Nice.
so that's what we do, and that's why it looks like super funky. But just
I see. But it's generated, so like nobody cares how it's formatted.
You're not supposed to look at it. You're supposed to run it.
Yes. Okay.
Yeah, it's good. Talking about the metagrammar, by the way, this is quite cool because the metagrammar is the thing that describes the grammar, and obviously when you write the grammar, something needs to parse the grammar, and that is another perk parser. It's called the meta parser, and yes, so it parses all the way. And we did this beautiful thing. If you go right now to the CPython repo, there is no parser written by hand. None of them are written by hand. All of them are generated. But then you say, man, this is a chicken and an egg thing, because like if the parser that parses the parser that parses the parser, like who wrote that parser? And it turns out the parser that parses the parser wrote the parser that parses the parser the parser. and how is that possible? Well, it's by the beauty of bootstrapping. What is bootstrapping? It's like if you have a compiler engineer, a friend that is a compiler engineer, this is what they secretly like. They don't like to be, hacked at night. They like bootstrapping. That's the thing.
Yeah.
So if you want to give them anything, give them bootstrapping.
It's like writing Go in Go,
yes,
and Rust in Rust.
Yes,
right?
yes. How is it possible? How is it possible that the compiler in C is written in C? It's impossible. Who wrote the first C?
Yeah.
This is the secret. Before, it was written in something different. So someone manually wrote, in particular, the first parser generator. And then, at some point, we did this process called lifting. So we make a parser so smart that it was able to understand its own grammar, so it could generate itself. And then once it generates itself, then you can destroy your handwritten parser, and all the parsers generate themselves in this beautiful process. It's also very hard to debug, but once you have it, it's magical.
Once you're confident it's good enough, then you can lift.
Yes. So exactly, yes. Now all the parsers are automatic, and this is beautiful. And that day was one of the happiest day of my life when I bootstrap.
So I wasn't particularly happy when we removed async and await, the soft keywords from our previous hacky parser and tokenizer, and then we happily reintroduced soft keywords with a new parser, because now there is no God. We can do whatever you want.
Yes, there is no law in this place. Only generated parsers. Machines don't think.
Yeah, so I was interested in knowing, like, okay, so if this is not so hacky and terrible anymore, how do soft keywords actually work in PEG? And what I discovered was it looks in the grammar deceptively similar. Only you have single quoted strings.
So nice, Łukasz.
And single quoted strings are the real keywords. And then you have double quoted strings. So those are the soft keywords. So
blobby keywords.
yeah, and like I have a soft spot for double quoted strings, so that makes perfect sense
So
to
if
me.
you run black over the grammar, then all keywords will be soft.
Yes, it's gonna be super slow now, right?
This is super confusing, man. Like so many contributors have looked at the files, like why there are strings with single quotes and why are there strings with double quotes? Like is there a difference? And then I was like, you're going to learn some dark truth here.
Yeah, it's a convention, but it is a convention that actually changes the behavior of the parser generator. So it turns out that with a soft keyword, what you have to do is you have to exercise the infinite backtracking. You have to try to extend the match that goes forward and forward, like with your input string of code, and see, like, does this match as a keyword? And only after that fails, then you backtrack and say, okay, this is clearly not a keyword because that failed, so let's just use this as a regular name. Meaning to me that whenever you have a soft keyword, that makes parsing all the variables that are called the same just a tiny bit slower.
Yes.
Because now you're going to always attempt to see like all those matches there, whether this is a keyword first.
So guess what rules are memoized? So if you have a keyword, better memorize that rule. That's why every time there is a new PEP that proposes a new soft keywords to solve all problems, then I'm like, wait a minute. It's not that trivial. There is some concerns here. So, there's a little, like, like a bunch of sticks holding like the dam of performance just with memoization and the trick. But yeah, it works. It's quite nice. Now it's time for what? For funky grammar secrets. Introduce nice music. Cool. Okay. First grammar secret. Cool. We are doing this fast. Okay. So the meta grammar will allow you to put like if something is memoized, and for that you write the rule name and then you put in between parentheses memo, and that allows you to think that, oh man, what else can I put here? Can I put memo, comma, something else? No. The entire parenthesis memo, close parenthesis, a single token. Surprise! You cannot put anything else. Actually, extending that thing to take more possibilities, which will be very cool because you could send more things out of rules. Like, for instance, the rule is invalid. That would have been great to put it there. It's actually a bit annoying to do, and nobody did that. So that's why I did this, like, starts with invalid. So that's how you mark them. Nice. By the way, we have this this thing, like we say, the grammar is there, and it will like you read the grammar and then you know how Python works because anymore you don't need to do this funky thing in the tokenizer and whatnot. Well, that's not fully true. There is some rules, only invalid ones. So for the real Python grammar, we are very strict. Only exquisite rules are added to the language, and we don't take bullshit. But for the invalid ones, it's free range. One of the things that you can do to decide if a rule parses or not is that you can do something very, very bad, which is called tokenizer feedback. Oh no, which is that the parser asks the tokenizer if a rule is valid. Oh no, man, coupling again like those people in black. No. So there is one single one. Is very difficult. Is one that is very hard to write, to be honest. Which is is a rule for invalid expression. They will try to tell you that maybe you forgot a comma. So for instance, you're writing a list and then you say X, Y. XY, that is an example. Then you maybe forgot the comma. So you wanted X, Y, right? So it will tell you, maybe you forgot a comma. And that will basically try to match two names, one after the other. But man, there is so many edge cases for this shit that is super annoying. So there is this little sparkling magic, that it will check that if you're at top level in the parentheses stack. So it will check that if you're in a list. So this rule doesn't work if you're in a list inside a list. Oh no, the secret has been revealed. But those are very rare. So normally people forget commas in top level. How we prove that? Because I say so. Yes. It's horrendous. Yes, another interesting funky secret, and this is the last one, I promise, and we will move on, is that you said, rules have this like thing at the beginning when you say the type, and this is very nice because like now the parser generator knows that this rule has this type, and it will put it in the compiler, and the compiler will yell at you if the type is wrong. Well, that is very new. Before, the type was void star. Yeah. Because C, as everybody knows, is a static language, and it's not monkey typing. Yeah, my ass. Like everything was void star, and then you could like magically cut stuff to stuff, and like the compiler was absolutely. I will happily cast this like expression to a, I don't know, number. Yeah, why not? Like, it's not that anybody made a mistake here. Like, they may compile it for you. And then it will crash. And that was really, really, really annoying. So I did this like crazy sorcery. I implemented generics in C. Oh no! So yes, I did. So there is this file in include internal PyCore ASDL.h. ASDL is this abstract definition language for the AST. Doesn't matter. But I implemented generics in C. There is like a bunch of pointer aliasing because like the standard says that you cannot like magically cast a void star to some other type and the reference as an array. That is illegal by the standard. So I have to like pay the price and do like a funky aliasing. But like now the compiler will every time you try to get elements for this generic list, will yell at you. It will say like no. This is like a expression and you cannot put a statement in an expression list because it's only expressions. And it's magic, and you can also lift, and you can say, no, let me treat this as a generic list. It has all sort of shit, and it will allow you to also do that. But you need to say unsafe, unsafe, like unsafe. Almost like what?
Like Rust.
Like Rust. I invented Rust before Rust. No. Actually, Rust was invented before this trick, but yes, and this is a macro, not a keyword. Well, anyway, that's it. That's everything I wanted to say.
All right. Okay. So let's finish with parsers for now. I'm pretty sure we're going to come back to them at some point, but 2 episodes in a row, I think that's enough. Now we're going to move to another section of the show, which is...
Ick.
Okay, and let me start with the weirdest PR that you can imagine, because it's a PR that actually doesn't execute anything, but it's very important because lawyers are involved.
Lawyers!
It's...
I like that you waited for the lawyers.
I knew. So this is an issue that we had since 2008. In 2008, somebody noticed like, hey, we have this standard library. It's called audioop.
Audioop.
So it has a bunch of audio-related transformations. And on top of that file, we have a comment that says, code shamelessly stolen from socks. Copyright Craig Lees, Joe Campbell, and Jeff Poskanzer, 1989. So in 2008, somebody was like, well... how about we don't have a file that says we shamelessly stole code? We should document the license under which audioop is actually used. And that issue was opened for years and years and years. And finally, some contributor appeared in 2012 and said, what about we use this one that is in Solaris and it's Sun Microsystems and it's the same file.
Sun Microsystems, oh, of course it's going to be safe.
Yeah, but at that point, 2012, like there was no Sun Microsystems anymore. But what about we use this license? But we didn't know. Like there was no actual lawyer to tell us like, is this the good one to use or not? And that issue was lying dormant for a long while. And then in 2020, somebody else came along and said, how about actually let's go ahead and just merge what is in that issue, what was suggested. But an actual lawyer was asked at that point, can you give us a thumbs up that this is what we should be doing? And that lawyer wasn't particularly convinced. There were some issues about, okay, there are links to where that code used to live, but if you actually go there, that site is defunct now. You cannot actually go back and check whether those links are correct. And there was some sleuthing involved to find what is the correct license. So at some point, a license was found and immediately used and put in the source code of Python 3.10. And it survived through Python 3.11 and through Python 3.12. And in Python 3.13, audioop was entirely removed. It was just dropped from the language because we already didn't want to maintain this ancient piece of code, which was very limited, somewhat buggy, not portable, and there were much better solutions for those sorts of problems on PyPI anyway. So in 3.13, that thing was removed. So problem solved, like it's still fine, right? Well, no. At this point, the most popular Python version on Earth is Python 3.10. So a lot of people see this newly added license to audioop, and there is some automatic tooling that is now scraping those licenses. And it found this weird thing in the license that we just put that said, no money shall be charged for the distribution of this code beyond reasonable shipping, handling, and duplication costs, and so on and so on. And this one sentence means, haha, we are no longer open source.
Oh.
Well, that sucks. This is not good. So another lawyer contacted the Python Social Foundation saying like, hey, like we shouldn't have this. Like, what is this? Now like our legal department is that Python is illegal to use at our company because it says no money shall be charged for the distribution beyond reasonable shipping. But our product is in Python and we are charging for it beyond shipping. So can you fix this? So we actually had to contact yet another lawyer to find out like what is the actual license we should be using and go on another hunt of what are the actual original sources. And we found that the original SOX thing that was referenced is Sound Exchange, that was originally part of a book about Sound Blaster in 1988. And since then, it actually grew into a larger library. And yes, Sun Microsystems relicensed it from the original author, so it's all good. So we could actually use that license. And I had to put this in to 3 very trivial pull requests and land them. But the story of this were like years and years of like legal sleuthing and finding like what is the correct thing to do, with legal departments saying Python is no longer open source because of a library we removed anyway.
Whoopsie. I guess the moral of the story is that if you involve some microsystems, something may go wrong.
Well, the moral of the story is that whenever you're saying like, why does Python remove things? Like, no, like we are removing things that are so old that nobody can really tell you anymore. Like, why was this added? How was this added? Who owns this? Like, sometimes really it is such a burden to keep maintaining things that removal is the only sane option.
Yeah, we want things to be open source, right? No, we don't want to track more.
Oh, yeah, definitely.
It's kind of important.
You have any PRs of the week?
Yes, I have one. So this is I'm going to keep the numbers kind of secret because I don't want people to know this is secret information. Only for the people who have survived 1 hour and 20 minutes into the podcast.
Okay.
So turns out that if you have used any of the cool profilers out there and debuggers for Python, such as PySpy or Austin or like PyStack or Memray or I don't think uses this, but also a
Does it
profiler.
qualify as cool though? No, I'm not sure.
Right. So it turns out that one of the things these tools need to do is that they need to kind of from outside Python. So these tools run outside the main process. They need to go into the memory of the running process to be able to profile it all the bucket and like just grab memory, like raw memory, and like extract it like brutally from there. And it's a very violent process. It's really, really hard. And for once you rip that memory from the other process, you need to understand the memory, right? Because this memory is like what it is. It's a string in Python, it's an integer, it's like a code object, it's a frame object. And then you need to understand this because you want to show like, the call stack or whatever the tool is trying to do, right? Profilers will fetch frame objects and it will tell you like what frame is calling what. So turns out that to do that, like most of these tools like copy the headers of all the versions of Python, and then they use like clever magic to see like, okay, what version of Python is running? Okay, so there has to be this header. So, this memory looks like this, and this is the number 3, right? Or something like that. Mm-hmm. But it turns out that those headers have become very complicated. And now it's very difficult to even if you have the headers, it's very difficult to know which version of the header is going to be, because you can compile Python in many ways. And depending on the way you compile Python, some of these things will be bigger or smaller. So now you will also need to know which way Python was compiled, which is not always possible. And some of these structs in the headers have 200 elements, or like some of them now are even automatically generated and have like thousands of elements. So you don't want to like copy things and like trying to match those things.
Right.
So in Python 3.13, we added a secret, well, it's not super secret, but it's just for this tool, so nobody really will use it. So we added in the Py runtime state, which is the bigger state that represents the whole runtime of Python, we added like a struct at the beginning of it that will tell you the offsets to the most common fields that you want to access. So things like the name of the code object, or like the frame object size, or like, where is the code object in the frame object, and things like that. And instead of like having the headers and having to compile them yourself to know the offsets, you can just, know that this struct is at the beginning of this place, and knowing how big is this struct, you can copy, and then you can learn from the process these offsets. And that is super cool. It's really nice. It was a nice thing that I did. So it was good.
Congratulations.
Yeah, but it was one problem, Łukasz. Do you know the problem?
I don't know. Bugs?
Yes, and nobody tested that. so it was the easiest PR to do. Like, hey, here's something, and zero test. So the problem is that to do a test, and people will say, "Oh, Pablo is doing things without tests." Like, no. How is this like? How is he a developer? Okay, yes. I'm a physicist, and I'm not a developer. Anyway, Anyway, Pedantic Pablo, right? So I did a test. And the test involves, why the test is difficult? Because the test involves literally making a profiler and using these things. But I did it. I did it in these secret PRs. And this PR basically implements a profiler. It's just something that starts reading memory from outside processes, which is a very funky thing to do, especially in macOS, because you need to do a bunch of like super barely documented function names that have like very weird names, and it makes you think about twice about your life and whatnot. But I did it, and the tool does the thing. And this is kind of cool, because this means, and this is the secret, Łukasz. This means if you're one of these cool people that listens to core.py and have waited until this moment, that if you import the secret module, because it's secret, it's underscore, because it's not part of the API, it's just for testing. So the module, you can call this cool function called getStackTrace. And then you can pass the PID of another process that has to be the same Python version, by the way. Profilers will work with all versions, but this has to be the same version.
Sure.
You will get the best stack, the Python stack, in a super efficient way. And you can use this to, for instance, without having to install any profiler, you can use it to debug a frozen Python program.
From another process.
Or you can put this in a loop and then you have built a profiler. Wow.
Nice.
It's secret, but I will not tell you the name of the module.
Because if other core developers find out that this is something that we maintain now, they will be terrified.
Yes, it's not, man. It's just testing. So if we need to remove it, we will remove it. Yes, maybe I will do a puff later. But yes, I will never reveal that the name of the module is called _test external inspection.
External inspection.
External inspection. Sounds very dirty, but yes, it's just for external inspection. The test, and you go, it's just insane. Like all these APIs, I hate them, especially the macOS ones were especially annoying to build. But the Linux one was easier.
So this test runs across platforms. It will run on macOS, it will run on Linux. Does it run on Windows?
No. But it runs on 32-bit platforms. And how do you know that, Pablo? It was fucking annoying, man. It was really annoying to make it run on 32-bit platforms. Because I ran the billboards and it was failing on Raspbian 32-bit. It's the only 32-bit thing that we have right now.
Yes.
And I discovered a bug in 32-bit platforms, and it was one of the most annoying bugs to the bug, because you need to run the whole billboard fleet just to know if the thing runs. And the problem is that I was using, this is very specific information, but it's kind of cool. I was using off_t, because I'm representing offsets. That's the type you're supposed to use in C to represent an offset. Off_t. The T is for type. Łukasz, question. How big is off_t in 64 bits?
In 64 bits? Well, it's 64.
And how big is off_t in 32 bits?
I guess it's not 32.
It's not 32, exactly. Good. You know what happens? That if you cast this to an integer, oh no, loss of precision. And then you have, do you know what happens? Like when you represent the number 3, how is the number 3 represented as a 64-bit integer? It has a bunch of fucking zeros. So if you cast that to an integer in 32-bit platform, your number 3 becomes 0. And what the special value is 0 also in C? Kind of like what pointer is this? It's null pointer.
Yeah.
Yes. So the error was you're the reference and null pointer. I was like, what do you mean? No, it's the number 3. What do you mean? And I was like, no, man, but this is 64-bit in both platforms. So
this is why C is now illegal.
Yeah, man. I was thinking on the US government quite a lot. So now instead of t is uint64t, which is 64 in all platforms, and it won't cast to integers when you do like integer addition to pointers. So that was real a bug. And the other bug was that I literally forgot one of the fields that was necessary to do the whole thing, and I discovered while implementing it. So now you know. Secret.
Oh, cool. Right. So let's move on to what everybody else is doing in this entirely different section of our show called
What's Going On in CPython?
These days, when we're doing this section, it's mostly three things that we're talking about. Free threading, also known as
No.
Then we talk about faster Python, also known as the things needed for the JIT. And then this third group, that is everything else.
Oh, that's a bit violent.
It is a little violent, but like
Miscellanea.
yes, misc. But it just seems that there is so much change in those first two categories, and it's so fundamental that it's just, like this grouping makes sense. Right. So the first group, free threading. And there are some meaty changes. What you have to understand is our last episode was the last day of January. We almost missed releasing in February, which would be terrible. But fortunately, this is the leap year, so we're releasing on February 30th. So we're golden. So there were a lot of changes in the meantime. The one that is the most impressive in my mind is how Sam added delayed memory reclamation called quiescent state-based reclamation.
Wow.
It just sounds super nice. Like, but, okay, what does this do? Like, why do we need this?
Quiescent.
Essentially, what you want to have is when you have concurrent accesses to some memory, you cannot free this memory while others are still looking at it. But at the same time, what you don't want to do is you don't want to lock reading access to some piece of memory such that...
The dictionaries, we explained this in the Nogil episode.
Yes. So what you want is to actually achieve parallelism there. So you need to delay the free operation until all concurrent reads are guaranteed to have completed. And this relies on this quiescent states. When a thread reports that it is not for sure in the middle of any non-locking read operations. And we have this fantastic place where we can actually do this report, which is the eval breaker.
Right.
Like we know for sure, okay, now no non-locking read operations are happening. And this implementation in particular borrows from FreeBSD's global unbounded sequences. Yes, not only licensing is very attractive to us for this, but the solution is also, well, Sam says, relatively simple, and we could build on top of this.
Relatively simple.
Yeah, like it's what Sam says in the PR, like, and I was like, okay, I believe you. Now the solution uses linear scanning, which performs well below 1,000 threads. So beware, users of Python. In Python 3.12, if you used 3, you would see, oh, I'm not actually using any of my cores. But now you can only use 1,000 cores. If you use over 1,000 cores, then this operation is going to be somewhat inefficient. So,
This language is stupid, Łukasz. Like, you cannot even use 1,000 cores.
What about all this CUDA boxes, right? Like all those CUDA cores. No, like for this, if this actual need arises, there are alternative algorithms we can use.
Like crashing.
Sam wisely recognized that, hey, for now, this is good enough. Like we have bigger problems to solve first.
Yeah, when I'm bigger, I want to be like Sam. It's cooler. Like I want to name something quiescent.
Yeah, quiescent.
Quiescent.
Yes, I also like this.
Yeah.
One bigger problem that we have with Nogil so far is that even though there is a configure option and there's a bunch of important changes towards it, we still don't actually disable the GIL. That is still not landed yet.
Right.
And the reason for it is that there are a lot of prerequisites to allow this. And one of those was to finish biased reference counting. So you might remember we said, okay, like the basis of this is already implemented in October, but there were two parts. Like the base change to reference counting was already landed, but there was one missing piece that was crucial. Because you might remember, like now there is no single counter for reference counts. There are two. There is the local one and there's a shared one.
Right.
And there are cases where the shared one, because it's shared, like it might get below 0. And in this case, you just have to say, okay, the owner thread of this object should reconcile this. So to do this, you need to use a queue to allow this inter-thread communication. And that queue was landed now. So that actually allows us, at least in this sense, to disable the GIL without crashes that some objects disappear too fast from memory. Yeah, and there were a bunch of smaller, well, I don't want to call them smaller, but like a bunch of other changes that allow removal of the GIL, like collections deck is now thread safe thanks to our new triager Matt Page from Meta. Donghina made free lists for dictionaries per thread, and Dino Wieland made the MRO cache thread safe, and also added critical sections over dictionary APIs. But that's no GIL for this episode. What about making Python faster?
Making Python faster. Ugh. So the biggest chunky PR was the initial implementation of trace stitching is now landed. We talked in the last episode about what trace stitching does. But basically, essentially, Python profiles your running code, and then it will discover what code that you're running is hot, and it can optimize, like, loops and things like that in numeric code. So in 3.11 and 3.12, we are already doing that, but this is done by bytecode specialization. So this is like when we replace generic bytecodes, like add things with like specific bytecodes, like add numbers that are integers with 62 bits or 64 bits, sorry. So, but now this is different, right? In Python 3.13, instead of doing this bytecode specialization, this will work instead by transferring execution for what we call tier 1 interpreter, which is the normal interpreter that is used before, into what we discussed previously, which is the new tier 2 interpreter, which, as you remember, is based on this idea of micro ops. And this execution to transfer happens via one API that we added called the executor, because it's a very specific name. Executor, it executes. No, it transfers. Because calling the transfer-uter, it was probably not going to fly. And this API basically consists of a linear sequence of micro ops, but can be basically optimized in an executable form. This is almost like machine code when you're doing JIT compilation. And actually, one of the ideas is that when you have these micro ops, you can actually run like a JIT when you stitch the JIT function. But that will come probably later. But basically, in this PR, after this PR, when the executor exits, Python also will track how hot those exits were, and they can attach new executor to those exits. And the idea is that once you do this, you can form an execution graph that you can also like optimize and decide which ones you can move away. Like if you enter and exit like multiple times, you can just remove that, for instance. So that's one of the biggest PR. I think that was Mark Shannon. It was Mark Shannon, right?
Yes.
Yeah, it has to be. The other PR that is important is that Ken Jin added basic type propagation and guard elimination on tier 2 optimizers. So guards are when you are checking like, is this you say this is an integer, is really an integer? So sometimes you can remove those guards because like you can prove that indeed it's an integer, so you don't need to do it. For example, if you have done it before. So if you have done it before and then you don't know that the type cannot change after that, then it's good. And oh boy, another thing that happened is that Mark Shannon added one interesting PR that basically implemented a change in the garbage collector called incremental GC collection.
Yeah.
And the idea here is that instead of like having a single collection that go through all the garbage in the generation, instead of doing that, because that's a long time and you need to go through all the objects in the generation and all that, we will talk in a different episode about garbage collection. It basically just goes through like a bunch of the objects in the generation just to reduce the chunks, and it just basically ensures that when you go and do multiple of these collections, you will end eventually going through all of them. That was nice. It was merged, but the GC doesn't like it. The GC doesn't like it. It's a very special guy.
Right.
And the GC rejected this change, and Billboard was failing.
Yeah, all the billboards were happy. One wasn't.
Except one.
Yes.
The big mem billboard that your friend Łukasz maintains in his
Yeah,
secret
I
room.
have it right behind me, and it sometimes gets a little warmer. That means Mark Shannon landed some diffs. And in this particular case, like it got really warm.
Yes.
Because it found some assertions that were failing.
Well, kind of important assertions like corruption and whatnot.
Yeah.
So we revert to the PR for now. Maybe in the future this will go back. In the GC incremental collection, the revenge. But until part 2, this is Roberto.
Yeah, so to be clear, like we're talking about this not as like some failure of, implementation. We're mostly talking about this for 2 reasons. First of all, those changes are tricky, and the testing with certain options and certain environments that we have needs to be really comprehensive to find edge cases in the transformations, in the mutation of the code base that we're performing. So the big memory build-bot, for example, this is one of those things where I get questions like, is this really so important? Essentially, every laptop now has a lot of memory. So what does it mean that something is really big memory? But it turns out like we have quite a bunch of tests that weren't even until very recently executed by the big memory build-bot, because even those tests wanted more memory than I would give them.
The mega memory billboard.
Yes, like that's the thing. So you need to understand like the build-bot has 128 gigs of RAM, but if you want to have any parallelism during those test runs, which you do want because you don't want them to take multiple hours, you cannot use 128 gigs as the limit for every test, because if there's going to be 4 executing in parallel, like, well, haha, you lost. Like, this is not how memory works. So I had to give them 24 gigs, and I thought that's enough, right? Like, that's a lot like to give. That's way more than any build bots actually are using. But it turned out no, there is plenty of tests that start with more memory than 24, and a lot of them require more than 30. There's still a bunch that require more than 50. And now I'm talking to Diego Russo from ARM like, hey, for those, maybe we can use your box that has 256 gigs of RAM.
Just add more memory. We
Yes,
just
like-
need to throw more universes to the problem.
I literally maxed out what the AM5 architecture in like a home PC can fit. 128 gigs is the max. There's not more. I ran it at a slower speed than the JEDEC specification because the AM5 doesn't support running it with full speed. But yes, in fact, the point is, this sometimes does find issues. And those are the annoying issues that Pablo mentioned, where you need to run it on somebody else's build bot to reproduce because it's just so much memory.
Yeah, that sucks.
And this is a particular tricky combination. And I did this kind of on purpose. This is not only our only build bot for big memory, it's our big memory Windows 11 build bots, and that's like a combo
What a
that
pain!
finds
What a pain!
that finds a lot
How
of
do you
edge
SSH
cases.
into that? SSH is forbidden technology in Windows.
I literally have another keyboard on my desk for this build bot because it's
course,
better
of
than
course.
any remote login.
It's easier to ask for a different keyword than to SSH. Okay.
Right. So just to call out those things, since this is becoming maybe the longest episode we had so far, let's just call out some other nice changes that happened this week, because it's not only no-gil, it's not only JIT and faster Python changes. One particular thing that I wanted to mention is not even really like a big code change, but it's like an end of an era.
Wow.
We had a documentation about how to port things from Python 2, and this documentation is now gone. The URL is still there if some existing links point to it, but it only says, hey, we used to have documentation here now, just look at those other web pages. It was deemed unnecessary for current Python documentation for Python 3.13, 3.12, and 3.11 to tell people how to port from Python 2 anymore. So that means the transition is essentially mostly done. Like, we are actually behind the hill already. We progressed. So this is one of those moments where the diff, the PR, doesn't really change that much. But if you look at it, you're like, oh, okay, time flies. We're over it. And I remember it was like, will we even ever adopt Python 3 as a community? Like, is this ever going to be over? Yeah, it's over.
Today is the day.
Yes.
Okay. we have something cool. The Python CLI help, when you run Python does that help, that it is. Now it looks much nicer. And you will say, well, what gives? Oh, this is a PR that, if I remember correctly, was from 2022.
Yeah.
Several years in the making. Wow. And what this does? Well, it turns out that when you run Python does this help, that was quite big. It was a chunky boy, like a lot of output, because it shows you all these like X options that have like a bunch of secret keywords that you can put there. And if you forget one letter, then it may not do what you want, and there is no warning. That's a story for another day, because I added a warning and people complain. So now there is a bunch of improvements. If I recall correctly, these were done by the one and only Sergi Storchaka. And for instance, there is a bunch of things now is much shorter. And also, like, lines are now squeezed. They are shorter than 80 columns, the best number, because there is not a better number, right, Łukasz?
Well, what's more important about this change is that this is now nicely indented. Like, the indentation is much clearer.
It's wrapped with the same indentation.
Yes.
And now I remove empty lines between the X options. And now it also is shorter because it hides all the like X options and whatnot. And if you want them back, you need to use does help that all the help. You need to ask for all the help. And then when you do that, then you will get a bigger output. And then it has also other things like help env and help X options. And you can check the help or different things. Yes. 2 years. Why it took 2 years, Łukasz?
I already said that in the PR when I reviewed it, and it offended some of the people who discussed there. It was in bike shedding hell, but I feel very strongly about ending bike shedding discussions, so I did that in this case, and we can move on to more important things. Like, for the longest time, we had support for the first Unix key value store, DBM, and there were many variants of DBM, right? The original one, and then GNU had its one, and BSD had NDBM, and so on and so on. And based on this, there still is, a shelf module where you can store arbitrary Python objects in this sort of key value dictionary on disk. Well, the only problem was that this DBM interface is really primitive when it comes to concurrent access, and the durability aspect of it is questionable depending on the platform. But most importantly, the files it produces are only usable for you locally. So it might be fine for a cache, but it's not going to be nice for reusing that file on another computer. So now, after years and years of us having this idea, and everybody said, like, wouldn't it be nice if we had a DBM backend that actually stores the data in a SQLite database? So we were talking about this, but not ever acting on this. But ever since we got an actual maintainer for our SQLite 3 module, Erland was great, making SQLite 3 feel better and more powerful. And now he got to a point where he was like, I can add the DBN backend for SQLite. He did. And the most amazing thing about this is that now transparently, Shelf can use it now. So even though you've heard this for years and years, that Shelf is just a toy, don't use it, use something else. Now you could probably actually use Shelf, it will be fine. And the reason why is you probably have SQLite in all your devices, like storing data for whatever you might think. Like your watch is going to store your steps and heart rate like in a SQLite database. So you might as well use it for your tiny use cases. So yeah, I'm very happy to see this, even though it's a maybe inconsequential change in the cloud age, but still for me very, very, very good to see.
Nice. Cool. Wow. 1 hour and 52 minutes. Probably it's a bit shorter because we will remove some blah, 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 but it's going to be the longest episode that we have ever done. How do you feel, Łukasz?
We should really think about making those episodes shorter from now on, which we will. But since this is the only episode of February 2024, it might as well be almost 2 hours.
Double. Well, anyway, the feedback so far has been from everybody is that they like long episodes, I suppose, because they love listening to us. Wow, incredible. So here's a 2 hour episode. What about this?
All right.
This is what you want.
See you next time.
Until next time. Cool. I'm going to click stop. Stop!